Welcome to Ready to Derive. In this video, we are going to learn about local linearity as it applies to differentiable functions and the process of linearization. So let me call up an image here. This is clearly not a differentiable function everywhere, but at x equals 2, it looks pretty smooth. It looks like it's differentiable, and I have created the orange line is a tangent line. Now, I've taken this from my video on equations of tangent lines, which you need to be able to write an equation of a tangent line for this video. So if you haven't seen that, please watch that first, and I will link it in the description. So I'd like to zoom in on x equals 2. So keep an eye on that red dot there, and as we zoom in a little further, you will see that the curve, the function seems to kind of flatten out almost. And if we zoom way in, the tangent line is almost indistinguishable from the function itself right there at x equals 2. So, and this is a very useful process. And why is it useful? Well, stay tuned to find out. Without further ado, let's begin.
So in order for you to fully appreciate the power of linearization, we have to take a quick detour, a tangent, if you will, pardon the pun. Yes, it's all connected. And I always kind of laugh at my students. Well, I don't laugh at them. I laugh alongside them when they complain about not being able to use a calculator on a test. And I say, wow, you guys just don't know how lucky you have it. Let me show you what I needed, what I had to use when I was young in school. Okay, so here, and yeah, I'm not that old, but let's just say I was in high school in the last century. That narrows it down a little. I had to refer to this booklet of common logarithms, and I'd had to use this to work out any calculations. So for example, if I wanted to work out the square root of 15, where the youth of today can just type it into the calculator, I actually had to use logarithms. And now you'll see why logarithms are actually so powerful, so useful. So I would have to work out the log of rad 15 first using this table. Now, why is that possible? You know, how does one use this table? So log of 15, that's really log of 15 to the half. And if we recall, the power of logarithms is that the property says you can write it as this. So I would have to work out half. So I'd use this table to find the log of 15. Now, so 15 is here, and 0.1761, that's not exactly the log. For some reason, you have to add 1 in front, and I can't for the life of me remember why that was. But anyway, let's just go with it. So a half of that is 0.58805. And then I'd have to go back to the table of logarithms and find 0.58805, which I'm trying this up. It looks like it's down here. So it looks like it corresponds to 38, and it's somewhere halfway between 7 and 8. So I'd have to write that out as, so those digits 3, 8, and then 7, 5, and then somehow, again, I can't remember how or why, we'd put a decimal right there and discover that the square root of 15 can be approximated by 3.75. Wow, a lot of work. So again, I always think it's funny when my students complain about not being able to use a calculator. At the same time, if we go even further back in time to the 17th century, to Leibniz, one of the co-founders of calculus, let's cut a page from his notebook. There you go. Talk about a complex calculation. He has a fraction here, and notice there's no decimals or anything like that. They weren't really using decimals back then. All that worked to kind of simplify a complex fraction. So, and I guess Leibniz would kind of laugh at me if I complained about having to use a logarithm table. So I guess it's really the same story over again. Anyway, what does this have to do with linearization? Well, that's what you're about to find out. We are going to use the equation of a tangent line to estimate the value of the square root of 15. So again, we are going to find the approximate value of square root of 15 by thinking about tangent lines. So let's just say, here's a square root graph. Again, this, you know, Leibniz never had access to being able to produce beautiful graphs like this using Desmos. We're so lucky. And let's think about, we don't know the square root of 15, but we do know the square root of 16 and that it's 4. So let's think, what could we do with that very important piece of information? Well, if we create a tangent line there, if we find the equation of the tangent line right there, then it seems likely that we could, let's see, if we want the square root of 15, we could take 15, the value 15, and plug it into our tangent line and get a y value that should be very close to, the value on the square root function, which is the red function. They look almost indistinguishable there. So let's try that. So we are going to find the equation of the tangent line at x equals 16, and let's call up the general formula for the equation of a tangent line. And then sort of set up all of the things we need. So we know f of x equals the square root of x, and we know that we're going to have, so a is 16, so I'm just going to put 16 in those places. Right, so we know we need f of 16, the square root of 16 is 4. We also need f prime, so maybe of 16, so I'm going to find f prime x. And you can do that, of course, you could rewrite square root of x as x to the half and use the power rule. I like to sort of get straight to the final result, which is 1 over the 2 square root of x, so you could prove that to yourself if you don't recall that. And then f prime of 16, we just plug 16 in, 1 over 2 rad 16, which is 1 over 2 times 4, which is 1/8. So our equation of our tangent line becomes y minus 4 equals 1/8 x minus 16 in point slope form. Now, because we're going to be using it to sort of estimate values, sometimes we isolate the y. So we have y equals 4 plus 1/8 x minus 16. So that's the equation of the tangent line. You might want to copy that down because we'll use it in the next slide. So let's begin by using our tangent line to estimate the square root of 15. So here's the equation of the tangent line with a convenient spot where x was. I can put 15 here, and that would be 4 plus 1/8 times -1. Recall that they used to work only in fractions in the olden days, so I'm going to write it as a fraction first, and then I'm going to take advantage of a calculator to say that 3 7/8, I've noticed the approximate sign, that's very important because we don't know the exact value. Oh, 3.875, that is exactly what we got using the common logarithm table. So not bad and a little more efficient. Let's see how we did. So if I use the TI-84 to get the square root of 15, it looks, and I went to 3 decimal places, so if we rounded to 3 decimal places, this would become a 3. So we're off in the thousandths. And that's not surprising because there would be deviation, but it's not bad. So let's try how to improve this is to actually, the closer we get to 16, probably the more accurate our approximation will be. So let's put in 15.5 here. This would be 4 plus 1/8, and that would be -0.5. And as a fraction, that would be 3 15/16. And as a decimal, that will come out to 4 decimal places. So we're saying this is approximately 3.9375. How do we do? Now let's go to 4 decimal places, and let's see there. So 9370, so we're off only in the thousands position. Actually, take that back, the 10,000ths position. So let's see if we can improve even more. Let's see if we can get the square root of 15.9, how accurate that is. So 15.9 goes there, which is 4, and it's minus 0.1 over 8. And if you, just as a little aside, if you wanted to sort of work that out without a calculator, multiply the top and bottom by 10, you'd get 1 over 80. So that's 3 79/80ths, sorry. And that works out to approximately 3.9875. Well, no, it works out to 3.9875, but we're saying that's square root of 15.9 is approximately that. Let's see how we did to 4 decimal places. So 1, 2, 3, 4. So if we round, since there's an 8 there, this would go up to 5, and that's pretty accurate. So that's the process of linearization. We're going to formalize that in the next slide. So the linearization of a function f at a, let's just put a function in here. Let's call that f of x. And we will call this, let's say that's a. Then we know that this would be f of a. And if we would like the equation of that tangent line, well, we know the equation from before is this. Y minus f of a equals f prime a x minus a. And what we do, though, because we're going to be using it, again, we isolate y and we write it like this. And because we're going to be plugging in different values, perhaps, as we did in the slide before, it's actually good to give this a function name, and it's often called L of x. So L of x equals f of a plus f prime a times x minus a. And that's the notation we'll be using moving forward. So for our first practice problem, I'm going to start off with a more straightforward scenario where we don't actually know the function, but we have enough information about it to be able to approximate a nearby the function at a nearby value. So let's call up the equation of the tangent line, or the linearization equation. Remember, in this case, a is 3. So I'm going to replace that all with 3. And we have f of 3 is 2, and f prime of 3 is 5. Sometimes people actually just distribute and simplify, so let's do that one time here, minus 15, so that will equal 5x minus 13. And now we are approximating f of 2.8, so it's important to put approximately. That will be approximately equal to whatever we get when we plug 2.8 in L. And that says to take 5 times 2.8 minus 13, and the answer comes out to be 1. So for our next practice problem, we're going to find this linearization and use it to approximate the cube root of 65. So here's the equation, and first let's replace a with, now sometimes, watch you don't do this, sometimes people put 65 in there instead of the nice number that we know, the cube root of 64, so don't make that mistake. You'd kind of figure out soon enough if you did, because you wouldn't be able to work it out. So here we go. So we have to get that information in there. And now I like to set up a little structure to help us make sure we have all the components. So here we would have f of 64 would be the cube root of 64, which is 4. By the power rule, f prime x will be this. And it's actually, because we're going to be plugging 64 in, it's actually useful to write it without a negative exponent like that. Then when we plug in 64, we have to do 64 to the 2/3. Now, you could do sort of any order, so you could square and then take the cube root, or vice versa, and vice versa is actually the way to go because you can do that in your head. So if you do the cube root first, so cube root of 64 is 4, and then square that, multiply by 3, you'll get 1 over 48. So this becomes 4 plus 1 over 48 times x minus 64. So that means L of 65, the linearization, would be 4 plus 1 over 48. 65 minus 64, which is 1. So it would be 4 and 1/48. And when you turn that into a decimal, that is 4.0208, 3 repeating. And we are saying that that therefore is our approximation of, or so approximately equal to cube root of 65. Let's see how we did. 4.02. I guess if we round to the thousandths place, they both round to 4.021, so not so bad. So for our last problem, I'm giving you not a lot of structure. So this could be a classic question you might see on a test or exam where you have to, no one's telling you the overarching function, nor are they telling you kind of the special value at which you do know. You kind of have to figure that out by yourself. So I hope you realize that the kind of overarching function is 1 over x. And that the special value, the nice value, so we don't know 1 over 102, but we do know 1 over 100. We can turn that into a decimal. So you identify the function, you identify the sort of nice value that you can evaluate the function at, and then you go from there. So let's call up the equation. And so A is going to be 100 here, right? And let's call up the structure. So 1 over 100 would be, so f of 100 is just 1 over 100. F prime x, sorry, if you write this as x to the minus 1, you'll soon realize that that would be negative x to the minus 2, which is negative 1 over x squared. So evaluated at 100, it would be 1 over, let's see, 4 zeros, so 1 over 10,000, negative 1 over 10,000. And then we can put these values in, minus 1 over 10,000, x minus 100. And so now we would like to plug in 102. So we get 1 over 100 minus 1 over 10,000, 102 minus 100, which is 1 over 100 minus 2 over 10,000. And you could get common denominators and what have you, but if we just turn this into decimals, just because we can, that comes out to 0.0098. How did we do? Hey, not bad, actually. That's 4 decimal places, or even you could even argue to 5 decimal places. We are correct. So before we end, I just want to touch on a concept that we won't treat in this video. It will be done in a later video, but just to kind of give you the heads up, when you have a function, look at the way the shape changes of that. That's kind of very significant. In the area over there to the left, you'll see that if you plug in a value, let's use a different color. Let's say if I plug in a value, you know, and I want to know the value of the function here at whatever this value, that x value is, let's call it x star, then when I plug that into the tangent line, notice that it's going to be slightly higher than the value, the desired value. And in this case, we say that the linear approximation is an overestimate. Let me spell that correctly. Similarly, in the bottom right hand of the graph, well, not similarly because it's actually quite different. If I plug in a value, let's see, x star, say x star is here, and I plug that into the function itself, if I want to actually know the function value, so that would be here. When I plug that value of x star into the equation of the tangent line, it's gonna be slightly lower than the actual value. So I'm gonna have an underestimate here, underestimate. And that all depends on the way the function is, the curvature of the function, and that's related to concavity and the second derivative. So we'll kind of revisit this topic after we've learned about that. And one more thing to be wary of, remember this only applies when the function is differentiable in the area that you're interested in. So for example, at this spot here, at that particular value of x, there's a vertical tangent line, the function is not differentiable, and the method of linearization cannot be used.
And that brings us to the end of this lesson. I hope you found it helpful, and if you did, please do click like and/or subscribe to my YouTube channel, Ready to Derive. Thank you.